Guys, hi. So we start our session. Today, Alexey Artemov will tell you about tips and trips of software engineering for data science. So please help yourself and follow him into the light.
Yes. So today we will be talking more about essential programming, not version control or any other related issues. So we'll more focus on the core code construction rather than doing anything that is sort of auxiliary. So let me start with a very short introduction into what we will be talking about. I've prepared just several slides, and then we'll basically dive into programming. And so okay, so let me share the screen. Hope you all can see the screen now. Let me turn on the play. So if anyone is not able to see the screen, please poke me somehow. So here's what we will be talking about today, and it's a very, very short introduction into various details of design decisions that you're supposed to make when you're coding. So in this tutorial, or maybe this lecture or this practical session today, I will talk about design decisions in software engineering, including idioms, principles, and patterns. So basically the overview, the agenda for today is we're going to first just a little bit talk about idioms, and so this is more or less to cover what are programming idioms and why they are useful, and then we will talk a little bit about language-specific patterns such as inheritance or encapsulation. And then design patterns, which will sort of be the core of today, and then the more general design principles. So I will not take a lot of time showing the slides. We'll more work with the programming, and I hope that we'll be able to basically write something useful, and that you will be able to actually pick up a few interesting tricks, although most of them should be picked from the practice probably. So often when you're programming, we unconsciously or consciously using something that's called a programming idiom. So programming idioms are small-scale patterns or small tricks that only apply to a particular programming language. So for instance, you can talk about C++ idioms or Python idioms, but not just idioms in programming as generally. So typically, in certain languages, some idioms exist, while they are basically absent in other different languages. So examples of a Python idiom, because I think that most of you are familiar with Python, are something like a dict comprehension, for instance, right? So the practice of writing Python code that actually takes advantage of idioms is typically, this practice is typically referred to as the code being Pythonic rather than being non-Pythonic. So for instance, if you are using this first line here to create a dict out of a list of tuples. Then you are sort of calling a dict constructor explicitly and passing a list of tuples into the constructor. So it basically builds a Python object for you. So this is a non-Pythonic way of basically doing this, because this is roughly the same way you would do it in C++, for instance. As for the Pythonic way of doing this, that is not really possible in most of the languages, is through this dict comprehension, where you are explicitly passing in through the curly braces a mapping the way it is declared in basically in well, when you are doing this in code. So if we go just a slide back, so these ideas typically are supposed to make your code a little bit more comfortable when working with a particular language. So for instance, in Python, not all of the operations are built into the language. For instance, this operation is built into the language, but say transforming list of dicts into dict of lists, it's not built into the language in any way, right? So idioms are small bits of code that are tailored to the particular language. So typically when programmers, especially when experienced programmers are trying to solve a problem in a particular language, they are using a lot of idioms without actually planning to use them, just because it's easier to use an idiom rather than not use it. This is one type of structures that I will be focusing your attention on today. Another part of structures that are used in design are decisions that are more or less specific to a particular design. For instance, lots of design decisions are for object-oriented programming, because this is one of the core programming paradigms these days. But of course, there are design decisions that are specific for instance, functional programming, or for declarative programming, such as the one implemented by the SQL language. So for the OOP, we typically have encapsulation, inheritance, and polymorphisms as one of the core examples of language-specific design. And not all of the languages have inheritance. For example, C, which is the language that was, well, it's still actively used in a lot of performance critical applications. It does not have inheritance or polymorphism, because it is not really object-oriented language. Okay. I will also draw your attention to that, as we will be going through a practical session today. The core of today will be the design patterns. So the design patterns are language, sort of more or less language invariant. They are more or less common solutions to object-oriented programming problems. However, it's not really about object-oriented programming. It's more about a particular class of programming. So, for instance, you can think of design patterns for functional programming or for declarative programming. But we will be working with object-oriented programming here, and with this kind of tasks. We will be working in the Python language. It's one of the the most easier languages to get used to, of course. And most of you more or less know Python, so it should be not too hard to grasp most of the terminology and everything. So more or less, design patterns are supposed to be reusable solutions to commonly occurring problems, right? So I will be showing a few examples today, and I hope I will be able to convince you that once you are faced with a particular task in programming and you are thinking about what is the best way of implementing this task, how do you solve this in code, that there are certain templates that you can use. These templates, you can code them in Python, or you can code them in Java, or you can code them in C or C++, and they're not generally language specific. And I hope this is why they are typically presented in several languages simultaneously. So, for instance, if you open Wikipedia and Google for search for design patterns, then you will find a lot of these patterns outlined in pseudocode, in Java, C, C#, and whatever language you prefer. And there's a bunch of books on design patterns. So I hope I will get you to like them, actually, because they are really helpful when you are developing a lot of code. These design patterns are in turn based on a bunch of design principles. So principles are less about, even less about particular languages or even paradigms, but they are more general. For instance, there is a particular instance of a design principle that's called "don't repeat yourself" that I will be referring to a lot of times today. For instance, it's true for all programming, okay? And so they don't really cover a particular implementation. They're more or less they more or less represent a guidelines to follow rather than specific problems. So I have seen people mentioning, for instance, that a particular pattern from the set of design patterns can follow a list of principles. And in the same way, one particular principle can serve as a foundations for multiple patterns or design decisions. So these design principles are more or less a set of guidelines. So there is a lot of design principles that people have invented over the last 50 years. And examples are solid, grasp keys, and a lot of other principles. So what we will particularly work on today is, I would like to make a disclaimer. So I have no intention of providing to you a comprehensive coverage of design patterns or principles or anything like this. So I will try to solve a particular problem as I was doing the previous time, except that this time I will be giving you more freedom in basically trying to solve it for a few minutes on your own, and I will be using a lot of these patterns or principles, and I will try to discuss it, and I will do my best to draw your attention to that. But the goal is to more or less draw your attention to the principles and what people have been using. And after that, I hope that you will be able to you will have enough curiosity to more or less read some books or some articles or some tutorials about patterns and practice it. So it's not too hard to actually start using it, but to start using it takes a while. So let me share a different screen. So I encourage you to open your favorite editor. To me, it's the PyCharm. So this is the repository that I have been using. So let us work today and code a small thing that is seemingly small. So one thing that we will code is that we will code a program that solves equations. So we will, of course, we will start with very simple, well, linear algebraic equations, okay? So I will do a main function for you. Okay, I will add it to Git, and maybe I will share it after in case you want it. But in fact, I have already pre-programmed the one I was preparing. So when you are thinking about solving normal linear equations, what do? So you start with a main function like this. Let's write a main function like this. So there is a main function that is a sort of, oops. So what do we have here? So we have two coefficients, let's say 4.0, and the second coefficient is -2 or something. So these hold the parameters for the algebraic equation that we would like to solve. So we'd like to solve a1 times x plus a2 equals 0. That's what we're going to solve, right? So and starting from that, I will draw your attention to a lot of tricks for the design patterns here. So what typically tend to do is they say, well, okay, so x is what? X is minus a2 over a1, and that's it. So let's print the result here. So the solution, I hope you will be coding along with me in your favorite editor, because it doesn't really take you a lot of time to program all that. To the equation, and let me code the equation here. So a1 times x plus a2, and I will be just formatting this for you. A1 is a1, a2 is a2. So has been computed. And the result is the result. X is x. Oops, so there's an x. So if you just run this, so let's go to work in progress. So let me also put inside here a shebang. So it's user bin yenv python 3, and I also will chmod plus x main py, so I could actually sorry, this zoom panel. So okay, so here we go. So the equation is actually, it's equal to 0, right? So what we typically have here, so here we're outputting this expression. Okay, so what's the problem with this kind of thing? So the problem here is that we see that it's this code is well, let's put it this way. We can characterize this code in a number of ways. So typical ways of characterizing the code would be, is it correct? This is the first quality of the code. So the code must be correct. All the rest that the code should adhere to is formulated like this. The code should be something, right? But the code must be correct, but the code should be something. Okay, so the code cannot be incorrect here. So as you can see, this is not a correct code, because if a2 A2 is set to 0, then this line will raise you an exception, right? But if A2 is 0, then we'll need to handle this as a separate case, okay? So let's first improve the correctness of this code, okay? So I hope you will code along, and I will comment as we do. So it's really easy to do this. So what is the case when A2 is set to 0? So it's 0 plus something is equal to 0. So if A1 is 0 and A2 is also 0, then we have an infinite number of solutions, right? So let us copy this over like this. So X is arbitrary. So here's what we have here, okay? However, if A1 is 0, but A2 is non-zero, so if A1 is 0 and A2 is non-zero, then there is a problem because there is no solution, okay? So there's something, so there's a non-zero quantity equals 0, which cannot be. So no solution exists. And in all the other cases, we're just computing in it, and we have made sure that in here we are not dividing by 0. We have a single basically solution, and I hope that everyone understands that. Okay. So in here, the code outputs the solution to the equation 0 times x plus minus 2, which sort of is creepy, but I will fix it later. So 0x minus 2 is equal to 0, so minus 2 is equal to 0, so it can be true. So no solution exists, and let us also check if the code actually works with this kind of coefficients. Okay, so the solution to this equation has been computed, and x is arbitrary. So this is correct code now. This is fully correct code for the linear equations here. Okay, so now what we have found here is that we have arrived at a correct code. Okay, that's not a problem, but if you look at this code now, here in the terminal, okay, so let us first also well, one thing that people typically want to do is they typically want to they want to input the data from a file. So let's open a file, input txt, read it as f, and so A1 and A2 is f.read strip and split, and then A1 and A2 are float A1, float A2. So in here, I have used a couple of Python idioms. The first idiom that I have used is this context manager. So I will be commenting this context manager idiom used. So what does the context manager do for me is it provides the way to automatically close this input.txt file once I no longer need it. So after this line has been executed. So this is one idiom I have used. And here is another idiom I have used, is that you can assign, so assign / unpack idiom used. So as you can see, we are really using language features here that are sort of well, providing us with utility functions. Okay, so let us also put inside a file input.txt, and inside that file I will just type in the space separated coefficients for the problem that we are solving, right? So now 5x plus 2 is 0, so x is minus 0.4. Okay, so let me also draw your attention to this fact that we have added the code to check for boundary conditions, so the code is correct. And now the code is organized in a series of statements. However, one thing to note is that we have used different solution strategies depending on the data we have. And we have ended up with much code redundancy here. So we are printing the result 3 times, and this is exactly the same code here. So this is breaks one of the fundamental code qualities that people typically want. And that quality is the code should be maintainable, right? So the maintainability of this code is harder to guarantee than the one when we only had, just this part of the code. And why is that? And this is because when I want to change one statement, so for instance, if I want to add to the linear equations here, I will have to do it 3 times instead of just 1 time, right? So let's go one step further and, well, more or less, make a function to solve so that's obviously a good idea to more or less extract this code that checks all these ifs. So that shouldn't be really in the main loop, right? So in here, we would like to actually call a function. So let us actually get ourselves like the solve linear equation here. So this is an obvious development step to make. So you're supplying it with the coefficients to the linear equation here. And, well, I'm letting the PyCharm to add the function automatically for me, okay? So what do I do here? So I would like to separate the computation of the equation, of the solution to the equation, and the display of the results of that computation. So this is one thing that people typically do. They separate computations from user interface. So these prints are actually working as a command line user interface. So a user can see the feedback when he's running computations, right? But this shouldn't be interleaved like this, okay? So I obviously need somehow to cut out. So let me copy paste this code here. So I'm not going to print anything inside the computation, of course, because this is ridiculous, okay? But what I would like to do is I would like to somehow indicate that my equation has either infinite number of solutions, so you can take arbitrary x, or no solution, so no x fits in, or a single solution, okay? So let me do it like this. So I will always be returning from that function some x that I have found, or maybe not found, and a solution underscore type. So this solution underscore type is a special string variable for now that will hold the type of the solution. So in here, x, and I will be using again this unpack assignment idiom here. So solution type, type. So if we are having infinite number of solutions, I will be, well, there is no reason to output any particular x here, right? So I will be outputting a non, but I will also be providing a solution underscore inf to indicate that this is really a particular type of a solution that has been found, right? That is not really a particular solution, but rather an infinite number of solutions in here. So I will be copying that here. And if the solution has not been found, so there's no solution that exists, I will be producing solution underscore non. And in here, I will do it like this. So solution underscore type is solution OK. So this is just a normal solution. So what I have done is I have made a function and made it actually return a specific value indicating which kind of a solution has been found. So let us support that in the main. So now this function, it actually returns a solution underscore type, and depending on that solution type, we will print something. So let me first rewrite this code like this. So the solution to the linear equation has been computed. So if solution type is solution infinite number of solutions, elif solution type solution underscore none, so no solution exists, else I will be just printing the value. Okay, so, and it will work in exactly the same way. Okay, so let me show you again what I have done. So in terms of imperative programming, what I have done. So I have introduced a bunch of conventions here in my code, so that if you are having the solution infinite here, then you're checking for this constant here, and you're producing the correct your user interface output. Okay. I have separated computation from the user interaction. Okay. And what the most important thing that I have done is that I have encapsulated the computation in that function. So you as a user, you don't really know what does this function implement if you are only looking at this signature here. So you're calling some function. You really don't know what it does. And well, people typically tend to organize such functions into libraries. So let me add a library. So I will just do it like this. I will cut this thing here, and I will just cut it out to a separate Python module to emphasize that this function is, well, sort of, you don't care about the implementation, really. You are only care about, well, its signature. So from solver, it's going to be like this, I think, import solve linear equation. So that should work in the same way, except I'm not a big fan of maybe it should be maybe like this. Yeah, so PyCharm doesn't like it this way, so I need to mark it as sources root, I think. So it could work. Yeah. So next step. So now, what has happened to the maintainability of my code here? So maintainability of the code has actually a little bit decreased. On the one hand, I have separated the implementation from the user interface. On the other hand, I have introduced these string constants. So if I make a typo somewhere in a string constant, then I'm screwed because, well, there's no way at this time that I could understand what exact string constant I should be using. There is no enumeration of this constant anywhere. It's just defined in the code here. So this is not a very good thing. Also, this can be referred to as coupling. Let me finish what I'm talking about. I'm gonna answer the questions that are being asked right now. So there is also such thing as coupling. So coupling refers to one part of the code knowing too much about the other part of the code. So this means that one implementation relies a lot about some other implementation. So for instance, here, we are specifically checking about the value of a particular variable, and we are specifically checking if this value equals a particular string. So we need to know that this particular string exists somewhere over here. So typically, there's no way that you, a programmer, will be liking this code, right? So this sucks, okay? So you need to go into source code and pick up the values of the variables. So this is called high coupling. So now the coupling is too high. So these codes in this main and in this solver here, they are too tightly coupled together. So we need to somehow in the future get rid of the actual coupling, of the actual reuse of string variables, because anytime you will be, you know, making a typo, it's basically exploding. Okay, so let me make a half-a-minute break, and meanwhile you can ask questions and I will try to answer them. Yeah, we can also, yeah, so Yarmek, I think you're right, and we should be doing like this, init py, so that it's actually a package. Okay. For the next thing that I will be doing here, so hold on for a few seconds, and I think we will actually, yeah, so input txt is just two numbers separated by a space. We will develop this equation solver into something nicer, actually. So the next step to do here will be this. So I'm gonna, to save time, I'm gonna actually share a code snippet with you, but I need a couple of minutes to actually put it on Gist, so that and sorry for the interruption. Gist, github.com. So the idea is, and let me show this with Rodrigo, I think. Rodrigo, can you please forward that into the chat, or if possible?
Yes.
Yes, thank you so much. Or I can do it myself as well. I can also posted. So what does underscore
It's already
underscore?
posted.
Okay. Well, okay. So I have also posted it on Zoom. So what does the underscore underscore init do? So typically underscore underscore init underscore underscore, what it does, it's actually turning your folder into a Python package. So in Python, what you typically do is you import from a package. So now this WIP.solver becomes so this WIP or the VIP is work in progress, the shorthand for work in progress. Okay, so it becomes a Python package. So you can do from the VIP.solver import
May
solve like
interject, I'm
this.
sorry. Concerning the question about modules and stuff like this. We will cover this topic the next lecture, but the gist of it is that standalone Python modules such as solver.py are already importable. You don't need a dunder init there. If you want
Okay.
to import something from a directory that contains other modules, but you yourself is outside that directory, then you need a dunder init so that
that's
Python
correct.
could understand that it's a package. That's it. You don't need dunder init right now in the WIP. If you want to import from WIP while you sit somewhere else outside of WIP, well, accessible directly to WIP, but outside, then you need a dunder there. But otherwise, it's not really necessary.
Okay. So this highlighted line is correct in this case, in my case. One thing that people typically work towards here is that they add different algorithms. So let's suppose that there exists, so this is a pure analytical solution. So you're computing it explicitly like this. So you're dividing one coefficient by another coefficient here. But let me show you a different solution, and we will implement a different solver here. So I'm just copy pasting this solve underscore numerical function, and I will be pasting it in the solver file, right? So what this algorithm implements is a very simple numerical method of finding the root of a function that that switches sign somewhere in a specified interval. So for instance here, because we are faced with a linear function, so it is supposed to go from the values below 0 to the values higher than 0 somewhere in the real line, unless the slope is 0, of course. So we assume that the slope is non-zero. So we define x-min and x-max that must hold somewhere inside this x-min, x-max segment. There has to be a solution to actually the problem to the problem of f of x equals 0, and our goal is to make this segment so tight that that actually the value of the function is below well, in this case 1 to the power of minus 3. So this is typically known as the dissection method of finding the roots of a function. So this is a high school numerical method of finding the root of a function, right? So in here, so what I will be doing is I will be actually adding this function here. So one extremely important thing here is that I can just simply, well, I suppose that I can simply replace the invocation of my solve function with my solve underscore numerical function here, okay? So let me now run this code again. So, and let me show that. So this is really working and producing me an approximate solution. So as you can see, each time the interval, so the first two columns here are depict the interval where the solution resides, and the last column depicts the value of the function. So as you can see, this bounds my solution within some segment, and the actual x that has been computed as a solution to this linear equation is pretty close to the analytic x, okay? Of course, it's not supposed to be equal to the analytic x because these are two different methods of solving the same problem. So I hope that everything works for you too. So what have we done actually? So we have provided a different method to solve the same task. So what's important here is that it's possible to interchangeably use methods 1 and 2. And also another thing to note here is that the solved numerical is actually, it does not really rely on the function. So if you look in the code here, what it does, it's really computing the values of the function. So it's not using the coefficients explicitly in this block, at least. But for the other blocks here, you have to still check. You have to still check if you don't have any solution, but you can implement this check in a different way. So it's actually interesting how you could do this. But let me actually again revisit the code qualities, the basic code qualities here. So we still have high coupling here, so because we still haven't done anything to this code, so we still are checking explicitly for the values of the string constants, which is bad. And we have lower maintainability, okay? And that is because we use the same checks in here as we used in here, okay? So we need to, if we wanted to edit this code, because these implementations are the same at this time, we will need to edit it twice. So twice the probability that we will introduce an error, okay? Okay, so let us actually go object-oriented, okay? So let us do it in a different way now. So because we are having the functions that are doing actually the same job here, so let me do it like this. Let me introduce a class. So this is what people typically do when they are talking, well, object-oriented programming. They basically introduce, well, classes. So what I would like to do is I would like to introduce a linear equation solver class. What it will do is it will actually solve. And you will supply it with a task. So this task is actually holding these A1 and A2 variables here, okay? So more or less what it will be doing is this, except that it will use this unpacking idiom and actually extract the coefficients from the task. So right now I am forcing this task to be a tuple with 2 elements, otherwise this line will actually fail. So this means that I no longer need this function because I'm having a class, so I'm safely deleting this. So I have just moved the definition of this function into a separate class. And then I would like to have a numerical solver sorry, numerical solver class here, and it would also have the same function here. So let me also cut it over here, and I will also A1 and A2. I'm going to unpack it. So it's as simple as that. So, and I'm just removing the unnecessary code. So one thing to note is that these two classes, they're actually having the same signature, okay? So this means that we need to have a base class for them. So notion of base classes is let me explain this to you. So because these two classes, they have the same function in here, okay? This means that these classes must be more concrete implementations of something more general. So let me extract this generality here. So, and this is why I'm actually doing this. So I need to do an abstract solver class here, and I will have to derive it from ABC, which is so from ABC, import ABC. For Python 3, there is a specific module called ABC that holds all the abstract implementations here. So in here, this particular method, it's not implemented, okay? And to make sure it is not implemented, and you cannot actually instantiate this class, I'm wrapping it into an abstract method. Oops. So abstract method. There was a typo. So this abstract method is a decorator, and this decorator is another pattern and language idiom for Python. So if you just try to play around in the Python console like this, copy pasting this code into Python console, then you will not be able to actually create an instance of this class, because this this solve is an abstract method. So you cannot directly instantiate abstract solver. So this makes this class abstract. Equivalently, this makes this class an interface rather than a particular implementation here. Okay. So I think there was some question. Right. So the abstract class is the class with abstract methods. So what people typically do, so what's an ABC? It's more or less, well, that's a good question. I really don't remember why we have to use this ABC here, but maybe we can get rid of this. So maybe we can just not use this class, and let's see what's going to happen. It's going to be possible to actually instantiate this class. So this ABC is required here so that you will not be able to actually create an instance of this class. Okay. Okay. What do we do next? So what I wanted to really do is I wanted to actually inherit from this abstract solver in both my classes. And why is that necessary? So this is necessary because I want each solver class to be compatible with the abstract solver interface here. So this means that I must specify an implementation to the solve method, to the solve member function here. But what is really important is that I will have to somehow reuse this code here. So these two conditions that I'm checking here, they are exactly the same. So this is where inheritance helps me. So instead of instead of directly re-implementing these methods, because this is ridiculous, okay? I have just created a class with all the same information, right? I will be using inheritance. So let me do it like this. So this linear equation solver, I will rename to the linear equations analytics solver, and this is the way it is in the handout that you will be getting after today. And what I will do is I will do a linear equation solver and descend directly from abstract solver like this. In here, I will move the implementation of the solve method, but here I will do it like this. I will call underscore do solve and pass in the task. Okay. So this is a non-existent method at this time. So I will need to create it. So I'm creating it. So this is no longer used. So it's going to call. So these two checks I will have to pass in any case. But this do solve is actually going to be invoked in a subclass. So now this do solve is an abstract method that one has to implement. So because you cannot use this class directly as well, because you don't know what the do solve does, but you are calling it, so you have to implement it. So now what we do is we have to inherit from linear equation solver rather than directly from abstract solver. And so PyCharm is actually suggesting me to implement the abstract methods, right? So it's going to be used like this. So how am I implementing an abstract method? So I will just, in the analytic case, what I just want to do is I would like to unpack the variables. And then I will be returning minus A2 over A1, because I am sure that in this case, the solution exists and is unique. So this numerical solver has a different implementation for that. Let me finish this implementation and I will actually provide answers to your questions. So we have a different implementation. Sorry, this is an underscore do solve. So this is a class that provides an alternative implementation. And what you do is you return X. So as you can see, I have just edited a few lines here. So, so where are we at this time? So we have created this class hierarchy for solvers. Let me finish discussing it and I will answer the questions if there are any. So this class hierarchy is actually, it's represented in one interface, which is very general. So it's like, you can think of optimization tasks rather than root finding tasks in these terms, right? So this abstract solver can be anything. You can derive optimization algorithms from it, for example, or something else. So this linear equation solver, it already does a few assumptions about the structure of this task here. So it says that this task, it's not that it must be a tuple, it must be unpackable, which means it must be iterable. So it does not have to be a tuple. So it can be, for instance, it can be a list. It can be a string of 2 characters. It can be anything. It can be a lot of things. So you're assuming this specific structure that it can be unpacked into 2 variables. and then it actually checks for the structure of the two variables, okay? But it has to rely on a particular implementation of the solver. So this solver is implemented into these two descendant subclasses. So the first is implementing analytic solution, and the second one is implementing a numeric solution. So these are two absolutely different solutions to the same task. But the code is reused. As you can see, we are having all this code is reused only once. So we don't have any duplication of code, which is good. We have higher modularity, which is also good. And what is extremely important is that we have a third quality of the code right now, which is extensibility. So a code should not only be maintainable, it should not only have high modularity, but it also must be extensible. And we have actually provided this capability. So right now, our code is more extensible in that we can add novel algorithms easily by adding novel classes. So this higher extensibility comes with class inheritance. So this is why the class inheritance is important in object-oriented programming. So let me answer your questions if there are any. What is the difference between linear equation solver and numerical solver? So as you can see, the linear equation solver is an abstract class that assumes structure about the linear equation, while linear equation analytic solver and linear equation numerical solver, they are actually providing exact implementations of the solution, and they are derived from this linear equation solver. So for those of you who are not familiar with class inheritance, let me just say a few words, and then I will refer you to the to any book on object-oriented programming. So what is class inheritance? So when you inherit, say, when you inherit analytic solver in here from linear equation solver, this means that all the code that is in the linear equation solver, that is all this code, is included in the definition of the analytic solver. So this derived class is also, it also has this solve method, and the implementation of this solve method is exactly the same as in its parent class. So in Python, the parent class is called the superclass, and the derived class is called the subclass. Yes, the linear equation solver then will be a common base class for the two types of solvers, for analytical and numerical. That is exactly as intended. One additional feature of the derived classes is that they can re-implement some of the methods that have been previously derived in their superclass. So in this case, this method is not implemented. So we must implement it. And that is what we do in both derived classes. So we can still inherit from linear equation solver and rewrite the solve method. That is exactly true. So if you don't want, if for some reason you need to re-implement the solve method, for instance, there's something you have forgotten about and you have understood that you need to rewrite the solve method. So this is, you can do this. And if you instantiate this, will be called when an instance of this linear equation analytic solver is constructed, is built. Yeah. So this class hierarchy is a tree of classes, really. So this at this time, this is a leaf of that tree, and abstract solver is some node in that tree, somewhere in that tree. Okay, so there is a class diagram somewhere. You can actually draw a class diagram, but I'm really not sure how to do this in PyCharm, and it has a lot of functionality. Maybe it's somewhere in here. I don't know. Class hierarchy, type hierarchy. Well, I'm not sure how to draw it, but it's possible. It's certainly possible. So okay. Okay, so how much time do we have here? Okay, good. So let us further work on the code for a little while, and then we will actually, or should we have a break right now, Rodrigo?
Yes, so why not we have so just a break and then we can move to the next section.
Let's break now, right?
Yes.
Yes. Okay. So let's have a break for maybe 10 minutes and continue at 10 minutes to 2. Okay. And I will mute until then. Hello, shall we continue?
Let's start.
Okay. Okay, so a question came during the break. So is there any case when it's okay to redefine the superclass method rather than inherit from the parent of that superclass? So typically when working with well, real-world applications, when you're developing real-world applications, you have no access to the code of the superclass. So it's possible to have access to the interface, which means you can derive from the interface, but it's typically not possible to modify the interface. So that means that actually is one of the core principles in object-oriented programming that's called the open-closed principle. So so classes should be, or code should be actually open for extension, but closed for modification. That means you cannot, in our case, then you cannot edit the definition of the interface here. What you can do is you can define a derived interface and extend this in some way. So when developing interfaces, it's really beneficial to be very general. So most of the interfaces are supposed to be general here. So let's move on, and I will advise some books about object-oriented programming later after this lecture is complete. So one thing I still really don't like about this code is that we still have manual coupling here, which is really bad, and here's why. So far, we have not used a lot of design patterns. And we haven't checked really the solvers. So let us actually import the analytic solver and the numerical solver, and we'll have to actually instantiate the solver. So the solver is, let's say, it's a linear solver, and we need to call solver.solve. Yes, both abstract solver and linear equation solver are interfaces. Actually, you can do something like this abstract linear equation solver to emphasize somehow that it's really an interface and not a solver itself. So now you cannot call it with two variables because it accepts really a task, but in a simplest form, this task is simply a tuple. So let us actually check this, and it works in the same way as before. So for instance, if this is 0, then it's producing you that no solution exists, and it works in the same way as before. So one thing I don't really like is that this is really what's called the spaghetti code. So spaghetti code is more or less like hard to read, obscure. It relies on certain quantities not defined anywhere. So this is something I don't really like. So let us move on with our OOP exercises and actually create a class that should represent you the solution info. So as you can see here, we know not only the the value of the solution. So that is, if you are solving 5x plus 2 equals 0, and you have the value of the solution, you also know that this is a normal solution. So this is not a non-existence of solution. And this is not an infinite number of solutions, okay? So this is a particular solution. So let me create actually a class for the solution. And I will call it abstract solution info. And I will derive it from ABC. And another thing that I will do here is that I will actually create, again, a Python file called solution info. Okay, and I will move this thing over here. So I'm gonna need the same, actually, the same imports here. So why do I need this kind of a class? So I need this kind of a class because I want to have not a manual examination of what the solver has produced, but rather a code like this. I would like my code from the solver to produce me a solution. And what I would like to see when the solution is when the solution arrives, I would like to just basically show it. And none of this code would exist. So we are going to end up like this. So as you can see, right now there's some common part to that, and the rest is dependent on the value of the solution type. Okay. So let me first understand what I need here. So I need some show method. Okay. So in this show method, I'm going to actually print this strings here. So I'm just copy paste that. So this means that this solution info object, it has to really have some access to the value, to the task actually. Well, because these A1 and A2, they belong to the task. So this means that A1 and A2 have to arrive from somewhere. So I propose to basically just organize it like this, create a constructor that actually will will assign the task into some member variable. So to do this, what people typically do is they just assign this to some member variable. So because in our cases, task is a tuple, so here we just assign to the task. But then the solution has been computed, but the rest is really dependent on the value of the solution, right? So this has to be implemented by subclasses. Like this. Okay, so this means I'm having really an abstract method that's called doShow, like this, that is not implemented in the interface. And I'm going to create an implementation of all these cases here. So class infinite solutions that derives from this abstract solution here. So it has the same two init and show methods, but it has a different doShow, because what it does is actually prints that x is arbitrary. Okay. Then we'll have another class that's called noSolution, and it also derives from this abstract solution info here. And in his implementation of the doShow, it says that, well, no solution exists. And the third one is called the normal solution. So that's not infinite and not none. So that also derives from the same thing. But here we actually have to somehow say what is really the value that has been computed, because we need to print it like this. So you need to copy it over here. But here you need to print it like this. So you need to know this value. And additionally, what I would like to do is I would like to maybe later I would like to have multiple solutions. For instance, quadratic equations, they have 2 solutions possibly. So what I'm going to do here is I'm going to overload. So I'm going to re-implement the init method here. It accepts task, but now it will also accept value. So for the task, I will just call a superclass. So it's possible in Python, and this is one of the idioms for the Python language. It's possible to call the method with the same name, but in the superclass. So whatever is done in the superclass in the constructor here will be done in this derived class as well. So you can, of course, if you would like to re-implement the show method here for me, so you can do it like this: super show self. I think. Sorry, it's not like this. Super self. Let me recall the signature. Sorry. Type and then the obj. So super normal solution self. Normal solution self. I always tend to forget it, but it's really easy to pick up. And then you will do where really a normal solution like this. So you can overload this function like this, or rather re-implement. But other than that, I need to actually save the value. So this value will come from the solver, okay? And here I'm holding the self value. That's all I'm doing here. Okay. Maybe the super class name self is not needed. I'm not sure. Maybe it will just work like this. But in this case, I really don't need it anyway. But so now it's possible already to actually get rid of all these string constants in the main. Okay. Because we have implemented all them in the solution info py. Okay, so our main function is super general, and it's really super clean right now. Okay, so this also, let me mark it that there is a super class call idiom. That's also from the Python language, and this I really don't need it. I did just to demonstrate that it's possible to do. So one thing to do right now is that we need to support it somehow in the solvers. Okay, so this solver should understand that there is some solution info and that it should yield solution infos and return solution infos rather than returning tuples or anything like this. So the way it's done is typically referred to an factory method design pattern. So there should be a factory method design pattern. So let me add a function. So this function is typically called something like solution underscore factory. So what it accepts is the type, which is going to be a string, and it also accepts arguments. So what it really does, it basically, depending on this type that I have passed here, it selects a particular class and creates an instance of that class. So this here is a factory method design pattern implemented. So let us implement that. It is extremely convenient in Python, because Python has native support for class pointers, and each class is some kind of an object in Python itself. So we are still having this solution inf. So that will going to point me to the infinite solutions, and then the solution none will going to point to no solutions, and then the solution OK is going to point me for the normal solution. No solution and a normal solution, okay? So what I need is I need to access the solution by type, because it's just a Python dictionary, it's just a map. I can put in the type here. So this type is expected as a string, and that's why I'm indicating here. And I will. So this is a class, really. And I'm putting this underscore after the class, because class is really a built-in in Python, a built-in keyword. So class underscore is the preferred way of actually creating a variable called class. So I will need to, well, basically return class underscore and put inside all the args. So a lot of Python idioms are used here. So first thing that's actually correctly asked by people in chat is that what the heck is this? What the heck is type underscore colon and then str? So in Python, you can suggest what type, at least in Python 3, you can suggest which type each variable has. So you can add type hints for this function, like this. So it's done like this. You can do type, the name of the input argument, then the colon, and then the type that it's actually supposed to have. So this type is having the string value. So this args is, well, I would say it's iterable, but it's typically a tuple. So here we use a Python idiom that any function can be declared like this: args, kw args. So, and it returns what it really returns is it returns an instance of an object that adheres to the abstract solution info interface. So this is a full specification of that. So we are using the args idiom in Python here. We are using the type hints, which is not really an idiom, but it's more like a language feature. We are using, so what we have here is we are actually using the idiom in Python that we have dict that points to any object. So mapping to any object idiom. And yeah, so this solution by type is one of the classes here. So these are pointers to classes. Okay, so this is an implementation of the solution factory here. So one thing to make sure is that this particular function cannot return you anything but the object of this type, abstract solution info. So anything that is returned from solution factory is guaranteed to implement this interface. This is due to the implementation. This means that solvers here, they can safely use this solution factory. So let us import the solution factory from solution info, import solution factory. So this solution factory will have to be so the solution is going to be constructed using this an invocation of the solution factory here. So we are now going to be returning only the solution object, which is holding the type of the solution that we have and the value if there is one. Okay. So let me copy it over and replace it, and it should be pretty quick. And here the solution factory is this, and you're also passing in the x, which is the value of the solution, and the solution is solution OK. So it goes like this. So as you can see, we still have the string constants, but now the string constants are enumerated here. So of course you can still break it if you are not very accurate, but right now all these constants are held in a single place, which is convenient for programming. So and there isn't a single there is no other place where we create solutions. So this function here is really working as a factory of solutions. So if you put it in natural language way, so this solver is a factory of solutions, which is the way it should be, really. So let us check if it works. So so this is missing one required position argument task here. Right, so it really should, yeah, it should really do task. Task should be passed in always, because it is expected. Oops, sorry. Should be done like this. So let me first run it. So this solution factory, it accepts a required positional, a required argument that indicates a string type of the solution, okay? And then optional args. So these optional args are passed to the constructor of the class. So you can really, well, you can really not pass anything there. So it's an optional argument, as you know from Python. Asterisk args depict optional arguments here. Yeah. So as you can see, so these arguments are passed to the class instances. So here are the class instances, and here is what they accept. So this normal solution accepts first is the task, and the second is the value of the solution, and all the rest are accepting the same as the interface. So so this is working now with the updated solution info structure. So I want to actually mention that all this that we are doing, these are only toy examples, and for this problem in real life, you might not need all this machinery behind, but this is convenient to get familiar with the notation and with what is being meant. So let us actually try and use this particular code to so let me also demonstrate that there's actually no solution exists, and if you are having a normal solution, then it works as usual, and so on and forth. So let us imagine now that what we have been told by our boss is that, well, now we are also solving actually the quadratic equations as well. Okay, so you all know how to solve the quadratic equations. So how about this? Let me actually, because we have worked around, we have played around with these solvers and with the solver interface for a while. How about I tell you that you have to extend this code for the next maybe 10 or 15 minutes, so that it also is possible, it will be also possible to actually solve quadratic equations. So what do you need to do this? Let me make you a draft for that. So now, because the quadratic equations generally have 3 coefficients and not only 2, then you have to introduce the possibility, but the same code should support solving both linear equations and quadratic equations here. So you can have either 2 coefficients and then this task is considered as a linear equation, and you can have 3 coefficients like this, and then this task is considered a quadratic equation task. So what you need to do first is you need to parse all the coefficients and check for the length of this array. Okay, so now you will need to check like this. If the length of the coefficients is 2, then you are treating this as a solution to the linear equation. However, if length of the length of the coefficients is 3, then you will need to instantiate a different solver, which is actually a quadratic equation analytic solver. But now you will have so these coefs are going to hold the task for you. And what you can actually do is you can really instantiate it without actually, you can really do it like this. You can only check for the solver and all the rest remains the same. And if length of the coefficients is neither 2 nor 3, then you are going to raise an exception, like say a value error, cannot understand the problem. So it doesn't know what the problem is, what the problem should be. So what you have to do for the next few minutes, and let me also use the least comprehension idiom for you. So we will actually iterate over the list for float value for value in coefficients. So now whatever the number of these coefficients, we will actually now it's let me that was previously used, and then here's the least comprehension idiom. So what you need to do now is really to implement the class quadratic equation analytic solver, and there's something you should import that from solvers, of course, and So in here, so as you might imagine, there's a problem with quadratic equations. It's that they can have more than one solution, more than one different solution. So you have to account for that somehow. And let me maybe give you 10 minutes, and you can use the discriminant and whatever you know. Let me give you 10 minutes, and so that you could try and create this class for you, and then I will do a walkthrough for you. Okay, and then we will have 2 more steps to actually finish for today. So you can ask questions, and I will give you time until 14:30.
Yeah, I have a question, but so you said that the original code that had this string constants for different types of the linear solution, the code wasn't good because you had to remember how these constants are written, and they are present both in a place where you invoke it and in a place where you use them, right?
Yeah.
What's the difference? Because right now, at least according to that definition, you have the same situation.
Yeah, well, there really is some cons or some problems with using the string constants, because what people typically do to get rid of the string constants altogether is that they create enumerations. And it's really possible to create an enumeration here, but I decided not to dive too much into that because it's more like a language feature. But you can do like something like this. You can do solution info, which is now a variable, and so you cannot be mistaken. So you can do a class like a solution type, which would derive from enum, and enum is a special type in Python. And you can do it like this: solution infinite is 1, solution none is 2, none, and solution OK is 3. And so what you could do is you could replace this here with a solution type dot solution infinite, and now it's no longer a string constant, so the interpreter is not going to forgive you for using the wrong variable here. And you have to support for here. So you need, of course, to know the solution type here. So the solution type is going to work like this. So like this, you're no longer able to make actually. So this is right. So it's no longer a solution type. It's a solution type at this time. So right now you're no longer forbidden for asking the. Well, you don't have to associate it with numbers. Probably you can do it like this, or maybe. But this is typically done with you must not associate it with numbers. You just have to provide some unique value for each of them. But this way you cannot be mistaken anymore, because the interpreter won't let you run the code unless all the types are in order here. Okay. So unum, yeah, it could be used with strings. You can do it like that. Inf, none, okay. As long as you have unique values here.
Is there any obvious way to do some exercises for OOP to establish this thinking? Because it's very counterintuitive when you need to basically have a solver that has only 2 or 3 possible options of invocation, to write the whole fully scalable hierarchy that you can infinitely scale, but actually for 3 solutions, it makes your code even less readable?
Well, it really depends so here we're only learning things, of course, but if you are absolutely sure that you are able to write the code and that it will remain readable in 2 years without you touching them, then I think you don't really need to introduce all that OP into the into the code in the first place. So, but typically, what this is about extensibility, and this is about maintainability, and this is about when new developer comes, and you don't really want him to, learn how you think, but you want him to solve a problem extending your code and supporting the way it works. But of course, well, in here it's a really toy problem. But mostly, so if you look into scikit-learn library, or if you look into PyTorch library, this is about big projects. So if you have a big project, so at least with more than 3 people working on the same code base, which is typically the case even for research projects, then this means that you have to maintain some kind of a code style. So this is one way of maintaining a code style, adhering to all these principles, idioms, and design patterns, because a lot of people tend to know the design patterns. Well, at least they're supposed to be good practices for coding. So we have 3 more minutes. Give me a few seconds. I need to grab a glass of water, and I will come back and continue with the quadratic equations here. Okay, so with respect to this quadratic solver, so if you encounter a quadratic, quadratic equation, what you need to do is to provide a special kind of solver, because the linear solvers cannot solve quadratic equations generally. So we need to provide a quadratic solver. So to provide a quadratic solver, we create a class in solvers that is able to actually implement the abstract solver interface. You can no longer descend from abstract linear equation solver, because these lines are generally not true anymore. So what you need to do is you need to provide abstract method. So in here, what we will do is we will basically provide the solve method, okay? So how do we solve quadratic equations? Well, quadratic equations are solved involving this notion of discriminant. So let me first do A1, A2, A3, and I'll unpack the tasks, and then I will need to compute the discriminant, right? Because this is the standard way of doing things. So it's A2 squared minus 4 times A1 times A3 here. So, and the thing is that the quadratic equations can still have infinite number of solutions, or 0 solutions, or 1 solution, or 3 solutions. Okay? And that depends on the values of the coefficients and the values of the discriminant. Okay? So when does a quadratic equation not have a solution? So quadratic equation. So let's start with the infinite number of solutions case. So when all the coefficients are 0, the equation does not have a solution. So instead of writing if A1 is 0 and A2 is 0 and A3 is 0, I am using this Python idiom A is 0 for A in task. So all coefficients are really 0. So this means that the solution, we need to invoke the solution factory, passing in the solution type, infinite solution, and passing in the task. So next, otherwise, we are checking for the discriminant, right? And this is the way I'm going to check for the discriminant. If the discriminant is negative, then we won't have any solution. Then we still need to construct a solution object by invoking this solution type, solution none, and passing in the task. However, and here's a modification that I will have to do, because, well, I will have to do this modification here. If all the rest, so 1 or 2 solutions go in the else. So if the discriminant is actually 0, which can be the case, so the values computed, well, this is actually a single value that is minus A2 over 2 times A1. And this is the default way of computing. So the value should be like this. And however, I will emphasize that this equation can have a set of solutions that has one element. So the set of solutions is non-empty and has one element here. And the rest, so in here we assume that discriminant is greater than 0. So what we do is we compute the set of solutions like this. So it's more or less like that. So it's minus A2 plus square root of discriminant over this. So you have to know what a square root is. So the square root, I'm going to basically import that from math. So now we have from math import square root here. So in any case, we need to still construct the solution object by calling the solution factory, solution type, solution OK, passing the task, and then passing the values. But as you have seen before, so we are returning the solution in any way. So this solution factory is actually creating us the solution info object. So the solution info object is really it really cannot work with the multiple solutions here. So I will need to somehow support it. So typically, what I should have done here is I should have extended the list of all solutions, of solution types, and I should have actually added somehow this. It's not a normal solution. It's like a set of solutions. I should have added another class. But but however, in here, I'm going to intentionally break this open-closed principle. So the open-closed principle from the design principle says that, well, I have to not touch the interfaces. I have to basically extend the interface. So what I should have done, I should have created a different interface and created a different concrete class, but instead of that, I will modify the normal solution here. And the way I'm going to modify it is going to be like this. So I will do it like this. I will create a list of strings to display the solution. So x underscore I will be equal to the value, and I will be formatting this. So I will be I plus 1, and value is going to be value. Sorry. For I value in enumerate self underscore values. So this is again a lot of Python paradigms at work, Python idioms. Sorry. So this I and value that the enumerate yields is one Python idiom about enumerating things and unpacking as you iterate over the list of tuples. Okay. A different Python idiom is the joining of strings using the string.join method. So let me comment out. So string join idiom. So recall that idioms are little code, tricks that help you get the most out of the language, and unpack as you iterate idiom. So as you can see, that doesn't really, break the code. So, and let me assign that somewhere like the out variable. And what I want to do is I want to do the print actually, or maybe I should just print it. Like this. So I'm trying to keep the code as readable as possible here. So all the rest remains unchanged. So this is the only piece of code in the normal solution. So all I did is I changed the type of these values here from a single floating point value to a list of floating point values, and that's it. So let me actually try. So this is no longer working because right now, yeah, I also need to support producing the sprint here. So what we do is we need to formulate the equation string that is also going to be like this, like use the same Python idiom here. So join a lot of strings with a space between them. So let me just do it like this. So let me, here could be coefficient, and it is going to be output with a sign. and then it's going to be a space, and then x to the power. And so I'm going to format it like this. So coefficient is going to have the value, and for the value for I and value in enumerate of these self underscore task. And the power is len self task minus 1 minus I. So this is just to display, to pretty print the equation. And that's pretty much it. So print plus equation string. So all I have done is I changed the print function. So this is no longer required. So now the equation is displayed like this. And I will also add the equal 0 for generality. So let us first actually, so we are now solving, selecting the solver. So let us check with a default value. So for instance, 1 minus 3 and 2 should have 2 solutions. One is 2.0 and the second one is 1.0. However, if we remove one variable here and we actually invoke it again, right, so I have broken, so this happens a lot of time if you play around with the interface. So I have changed the interface for the abstract solution info, which I shouldn't have done according to the open-closed principle. So now I get punished for that, because now I have to also update the interface for the numerical solver and for the linear analytic solver here. Because they now have to be compatible with this interface. Luckily, it is really simple to do, but this is why the open-closed principle is always at work. So you can't do this, really. Okay, so here we have come to a code where with a few lines of code, you can solve a lot of problems, display them, solve actually two problems, but this is extensible, as you can see here. You can add a third, solver or anything. You can have numerical solver, or you can have quadratic solver, or you can have linear solver, depending on the task. So you can actually select a solver. So this actually that's one extension. So now let us extend this code once again. So as you can see, so now we have actually in both the abstract linear equation solver here, we have to check somehow that the solution does not exist. And in here, in the quadratic equation solver here, we also have to check that the solution does not exist. And in both these classes, we have to check if there can be infinite number of solutions. Okay. So why don't we use another design pattern that is called the template method? So let us use this pattern like this. So this abstract solver, I'm going to actually extend this this actual implementation in these ways. So I'm going to remove actually remove the abstract method of the abstract solver. So, and I will further proceed like this. So I will write a pseudocode for now, and you can just watch it. So we can check for infinite number of solutions using this task. And if we do, so if this check inf solution should be some method, and I'm adding this now, and this is an abstract method. Otherwise, we are checking if there are no solution, and this is another method, and it's also going to be abstract like this. However, if otherwise you do the values you compute using the self do solve, and you pass in the task, and the solution is going to be like this. So you put on the values, and then you just return the solution. So this is important here because now, and I'm also adding the do solve, and I'm also denoting that this is an abstract method. So as you have seen, so this solve is organized in the same way in all of the solvers that I have been using so far. So it has the same template structure. So this means that why don't I create a specific solve function, and inside that solve function I will rely on well, basically on implementation provided by the subclasses and not on the not on the implementation that's actually in the base class. So the template method is a method, it's typically in the superclass. So we have provided this method, this solve is going to be a template method. So this is an abstract superclass here. So this method is basically defines the skeleton of some operation. In this case, solution to the equations, to the system of the equations. However, this skeleton is defined in terms of a high-level steps. So each of these steps can be implemented by additional, well, helper methods. So these three are the helper methods in the same class. So these helper methods, in this case, they are abstract, in that they are not implemented in the abstract class. However, I could have implemented some of the methods in abstracts class. For instance, I could basically, well, I could have implemented this check inf solution like this. If all a equals 0 for a in task. So this is no longer an abstract method. Of course, if the task is a linear or a quadratic equation and all the coefficients are 0, then there's no need to implement anything, okay? So that makes a lot of sense. However, we still should check for the existence of the solutions in each of the concrete of the derived classes. So now we do not have the solve method here. What we instead have is that we need to actually well, implement all these methods, the check for solution methods. For instance, how do we check for solution? So check no solution, sorry. So and the do so at least in here return. So what you do is you unpack this. So I'm rewriting this class hierarchy for solvers here. This is typically not, so we're not supposed to sort of do this. However, I'm doing this to show how you can refactor your code. So in this case, because this solve method is already implemented in the base class, I need to remove it. This doSolve is not implemented in the abstract linear class, so I can remove it because it now has been moved one way up, all the way to the base class. And here, these two methods, abstract linear equations, linear equation analytic solver, and the numerical solver, they basically provide implementations of the solve method. And the quadratic equation solver, we need to implement all these methods. So I'm adding implementations. So in here, you have to check for no solution by computing the discriminant and checking if the discriminant is less than 0. And what is here is you don't have to do with any of the solution construction and things like that. I'm just moving the definition of the solution here, and you're just returning the values. And I'm removing this. So the solution factory is this. So let me quickly reiterate on the refactoring that has occurred right now. I hope that you were following it. So what I have done, so first I provided a template method solve here to solvers. The problem with this refactoring is that we have violently violated the open-close principle. But nevertheless, now the abstract solver implements the following skeleton. It checks if there is an infinite number of solutions, and by using this check-inf solution function, then it checks if there's no solution using a separate function, and then it actually solves. If it is sure, then there is some solution to the problem. Okay, so these subclasses are required to implement all these methods. So you can implement them somehow. So for at least for instance, this abstract solver is already implementing the check-inf solution for you. So you don't really have to re-implement unless you have a better implementation for that, or a separate implementation. We have violated the open-close principle because we have changed the interface. So there's no way you could change the interface normally. There's no circumstances where you want to change the interface. For instance, think about if you are working with scikit-learn and somebody just changes the interface of an estimator, which is a base class for everything in scikit-learn. So, for instance, there's no more fit function. So how are you supposed to use it now? So that's what we are doing is we have actually added a few methods. So all these solvers now are forced to implement all these methods. So this is not a normal thing. Really, that shouldn't happen too often. Otherwise, your code will get too, actually too dirty. Okay. Okay. So we have provided these implementations. So that's called the template method design pattern. So that's one of the design patterns that is actually in use, one of the design patterns that's often used. What we have also noticed that actually it's now a high quality code because it has high maintainability, because there isn't a single line that is being done twice, or except for the computation of the discriminator, which sort of is an internal computation by this class. So you might want to pre-compute the discriminator here, but let's forget about that for now. It is highly modular and it's highly extensible. So it's really easy to extend it to a different class. And let's see if it still works. And it's still working, which is important, of course. So right now, I still have a few minutes, actually 30 minutes. And let me also show you a different design pattern. The last one for today. So it's really easy to actually you can do whatever you want as long as you are the only user of the library, okay? But this is not normal. If you are the only user of the library, then probably you are doing something wrong. Then you're just writing some code just for yourself, just for fun. So this means, and it's also, it's really normal to refactor a lot in the beginning of the development process, because typically in the start of the developing process, you have no idea about what the final library will look like. You have only a rough idea about this. So this means that you will have to actually refactor and change interfaces early. And this is common to a lot of big libraries. For instance, PyTorch used to change interfaces a lot of times at versions 0.1 and 0.2 and 0.4, and they still break interfaces in a number of ways when they release code. However, you're actually they tend to be stabilized a lot. So let me also show you the last design pattern that is called strategy. So strategy is another design pattern that implements a particular behavior. So as you see, these solvers here can be used interchangeably when you know what type of equation you are solving. For instance, if you find out that you are solving this equation, it's possible to actually use if you are solving linear equations, you're using this linear solver, and if you're solving quadratic equation, you are using a different solver. So what I will do now is, and if you are having a lot of possible algorithms, then it's sometimes useful to actually hide which algorithm is being used somewhere in a different class. So let me actually do like this. So let me create a class. It's going to be a really simple class with only 6 lines of code, and I will call it equation processor. So what it will do, it will initialize with a solver already. So it will going to have a solver inside it. Sorry, it's a solver. Then it's going to actually have a set solver function to be able to actually replace the solver. And it will also have this solve method. And it also will have the task. So what it does, it's really returns self solver dot solve task. So whatever is the current solver here, it is going to be used to solve the task. So this solver has to adhere to the abstract solver interface. So you may want to indicate that like this. So you may want to do it. You may want to import the abstract solver, and you may want to show that this has to be an abstract solver. Okay. So what I will do next, I will create a lot of solvers. So I will create a linear solver, I will create a numerical solver, and I will numerical solver, and I will also create a quadratic quad solver. And instead of actually invoking each solver separately, what I will do is I will actually create a processor. So the processor is going to be an instance of this equation processor class, and for the solver I will basically put inside well, let's put a linear solver for now. Let's put a linear solver. So the thing is, what we want to do is we want to actually, instead of selecting the solver manually, what we would like to do is to always call processor solve, which will need to create the solver somewhere inside. Okay, so more or less this is achieved. So using this, so what you really can do is you could really create. So once you have, let me show let me show it like this. So as you see, this is a very subtle change. However, you can always processor set, you can always invoke this processor.set solver manually and put in a numerical solver, or you can do with a quad solver, or you can then go back again to the linear solver if you needed to. So all these algorithms are actually used interchangeably somehow. And these, so you can substitute one algorithm for another. And in this case, you are able to select an algorithm at runtime. So instead of implementing a single algorithm directly, so this code receives runtime instructions about what particular algorithm in a family of algorithms to use. So this means that actually this strategy pattern, it really lets the algorithm vary independently from the code that actually uses this algorithm. So as you see here, so this line processor solve is invariant So it stays the same no matter which solver gets selected. So of course, this is a very simple example, but this is the way it is done. You can think of a extremely much more complex business logic behind the selection process. So for instance, you may look at the coefficients and assign dynamically the numerical solver if you believe that the numerical solver is going to be more efficient for you. Or you can understand that certain solver is non-applicable. For instance, the quad solver cannot solve a linear problem for you. And numerical solver, if done correctly, it can solve an arbitrary function for you. So this solver is really, it's possible to select it at runtime actually, and then assign it somewhere in the equation processor, and then actually solve. So, of course, it is going to work in the very same way. So, for instance, for this linear equation, it should work in the same way because it's just the same code is being called. So this processor is just a wrapper around the solver that enables substitution for a different task here. So we are approaching the...
Alexei,
yeah,
we're now over time actually, so maybe let's just say final
Yeah.
words and then we can
yes,
conclude.
thank you. Okay. So basically, the final words are these. So I hope that with this toy example, I was able to actually demonstrate how actually convenient and extensible a code may become if you're actually using this, object-oriented logic behind it. So there is maybe several dozens of design patterns out there, and I encourage you to find out more. So the general book for the design patterns would be called the design patterns : elements of reusable object-oriented software, and it's freely available, I think. And also there is a head first design patterns, which is extremely useful if you are starting to dive into these. So head first series is an excellent series of books. So I hope that you became at least a little bit interested in using the design patterns and actually consciously selecting the pieces of design that you will use to build your software one part at a time, and that you consciously and that you crisply understand what will be the consequences if you choose to for instance, change the interface of the abstract class, that you will have to, rewrite some portions of code elsewhere, and break dependencies and things like that. So that more or less concludes concludes this tutorial. So we will release questions later today, and we will release the codes and the presentation for this tutorial. And I will do my best to, add a bunch of references to code and to books there. Thank you.